Bismillahirrahmanirrahim. We are looking at the next concept now, which is carrier sense multiple access with collision avoidance. In the previous video, we looked at why we need carrier sense multiple access with collision avoidance instead of collision detection. And this was because in wireless networks, it is quite difficult to reliably predict or detect the collision. We can't detect the collision as easily as we can in a wired network. And because of that, now we have to come up with some way in which we can avoid the collision instead. Okay? We'll have to avoid the collision instead of detecting it. Because as detection is not very reliable, we say instead of detecting it, we will now find a way to avoid it. Okay? So this is carrier sense multiple access with collision avoidance. In the MAC layer in wireless LAN, we have two different types of functions. Okay, we have the point coordination function and we have the distributed coordination function. For your syllabus, you have to look at distributed coordination function. And in the distributed coordination function, we're dealing with multiple access. And remember, what did we say about multiple access? It is the process in which more than one device will try to access the shared medium, right? And in this case, we have the air space that is now being shared with different wireless devices. And we are looking in CSMA, we employ two mechanisms, which is explicit acknowledgement. So we are looking to receive an acknowledgement for every data packet, any type of packet, mainly data. Data packets would need acknowledgements mainly. So we're looking to receive acknowledgements for the information that we send. And we are also looking at exponential back-off. So what is the exponential back-off scheme? It is very similar to the process that we did in Aloha. Okay, so we have, in this case, we said that initially the value of k, we had put it as 1, right? And when k is 1, you're choosing between 0 to 2 to the power k minus 1. So you're choosing between 0 and 1, we said, right? So what is this? Exponential back-off. It means that every time the packet fails to get sent, we are going to choose a value between the range that is given. Okay? In this case, the range is 0 and 1, okay, for k is equal to 1. So when a back-off takes place, we said the back-off time is chosen between the range 0 to w minus 1. And in here, w can be considered as 2 to the power k, where k is the number of attempts, we said. So it is something quite similar to what we studied in Aloha. So as you remember, we have now k, when k is equal to 2, we are saying it's between 0, 2 to the power 2 minus 1, which is 3. So now the range is 0 to 3. Okay? So look at what's happening. In here, the choice is 2. And in here, the choice is 4. And then when k is equal to 3, what's happening to the choice? Now this is 0 to 2 to the power 3 minus 1. So you have 0 to 7. So the choice now, the range is 8. Okay? The choice or the range that we have available to choose from is 8. So every time there is a failure in transmission, what happens to the back-off window? It doubles in size, right? It doubles in size. This is called, and why are we doing this? Because we are saying that a device will wait for a certain time. And what is that time it will wait for? The first time, it will be given a choice between 0 and 1. Okay? The back-off timer would be between 0 and 1. The second time, now because there has already been once a collision, the device will be given more choice. So now the device can choose between 0, 1, 2, or 3. One from these numbers. Again, if there is a collision, the device will now be given k is equal to 3, and it's given more choice. So as you can see, the devices are being given more and more choices, and this is so that the more the number of choices they have, the more it is possible that they will not choose the same number. They will choose different numbers. Okay? So exponential back-off means that when a back-off takes place, the back-off time is chosen between the range 0 to w minus 1, where w is to the power k. After each unsuccessful transmission, okay, now that's important, unsuccessful transmission, every time you have a packet that fails to get transmitted, we have the back-off window size is being doubled. And we saw that first the size was 2, and then the size was 4, and then the size was 8, and so on. So it's doubled up to a certain maximum value. And the value of W is reset after every successful transmission or when the retry counter reaches its maximum limit. So when we give a back-off window to a device to choose from, the device will now choose a number from these, okay? Will now choose one number from these, and then it will wait for that amount of time, okay? It will wait for that time. So if it chooses 5, then it will wait for 5 time slots. Okay, it will wait for 5 time slots before it goes off and begins the transmission. But it doesn't just wait. Now there is a specific way in which the device waits. Okay, but before that, we have to just wrap this up. Okay, so this is the exponential back-off scheme. Okay, so remember, this is called the exponential back-off scheme. This whole thing is what happens in the exponential back-off scheme. So the DCF mechanism, distributed coordination function, it has 2 modes, the basic mode and the RTS-CTS mode. So let's look at the basic mode first. Okay. In the basic mode, now before that, let's look at this definition here, DIFS. Okay, a times frame called DIFS. What is DIFS? It is the distribution coordination function interframe space. Okay, DCF interframe space. Now, a device, when it wants to send, okay, so what is DIFS? It is a time period, okay? This is a certain time period. Now, the sender, when it wants to send, it will first listen to the medium. It will sense the medium and it will make sure that the medium is free for this time, DIFS time. Okay? If the medium is free for DIFS time, if it is the first time it is sending, it will only wait DIFS. If it has been more than once, or if there had been before a collision or something, or the medium was busy, then it will also add the back-off timer. But if it is the first time, then it will wait for DIFS time. If the medium is still free, then it will send the data. Okay, it will send the data. Then after sending the data, it will wait for a very short amount of time, okay, which is called SIFS, short interframe space. Okay, short interframe space. As you can see, this time space is very short compared to DIFS. What does this tell us? This tells us that the acknowledgement packet that is going to arrive after the SIFS time, which is a very short amount of time, this packet is of a high priority because we are not waiting a long time before sending it. We're waiting for a very short amount of time. So this shows urgency. This shows the packet is relatively more urgent. Okay, this is an urgent packet. So it has a high priority. So the SIFS time is the short interframe space. So the sender has waited for DIFS and maybe back off and then sent the data. Then it will wait for an SIFS time. The receiver also, because it has successfully received the data, it will also wait for an SIFS time, and then it will send the acknowledgement packet. Okay. And when the acknowledgement is received successfully by the sender after the SIFS time, it means the transmission was successful. And then again the process is repeated. The sender will wait for DIFS time and back-off time if needed, and then send another packet. Okay, so this is about the basic mode. Now let's look at another scenario here. Okay, in this scenario we have three machines. Okay, we have Sue's machine, we have Arnold's machine, and we have Mira's machine. Now Sue's machine decides to send information to Arnold's machine. So what are we doing now? We wait for DIFS amount of time, back-off time, and then it transmits the data. Okay, it transmits the data. But while the data is being transmitted, Mira's machine wants to send some information, wants to send a frame. But when Mira's machine senses the medium, when it listens to the medium, it finds it busy, right? So now the machine will wait until we receive the acknowledgement, okay? Until this time, it will wait. It does not send anything. And then what did we say? What happens when the machine finds the medium busy? Or rather, when do we use the exponential back-off scheme, we said? There are two times when we use the exponential back-off scheme, and that is either the medium is busy or when we do not receive an acknowledgement. Okay, 2 times that we use the exponential back-off scheme. When do we set the back-off timer? Number 1, when the device found the medium busy. Okay. And secondly, when device does not receive an acknowledgement. Okay, 2 times when we use the back-off scheme. So now in this case, because Mira's machine found the medium busy initially, after the medium becomes free, it does not send the information. What does it do? It will wait for a DIFS amount of time first, right? And then what will it do? It will wait for a back-off time. It will start the back-off timer. Remember, we showed the window, so we had the set of values. Mira's machine has now chosen a number and it decides to wait for that number, okay? The back-off time. And how does this back-off time function now? Okay, so let's say the back-off timer was initially 8. The machine will listen to the medium and it will see, is the medium free for a DIFS amount of time? If the medium is free, then it will decrease the counter to 7. Again, it will check the medium for DIFS amount of time. If in this time the medium is free, it will reduce it to 6. Okay? Now, let's say at this point in time, after when the timer is 6, let's say it finds the medium busy. What does it do now? Okay, if it finds the medium busy, it will not reset the timer. No, it will freeze the timer. Okay, the timer is now frozen at 6. This does not change. And it will keep on listening to the medium until the medium becomes free again. Okay, and for how long should the medium be free? To make sure that yes, it is free, we said it should be free for 1 DIFS time, right? The medium should be free. When the medium now becomes free for 1 DIFS time at least, now the counter will go back to 5. Okay, and then 4, and then 3, 2, 1. And then when the timer reaches 0, it will send the data. Okay, so this is how the back-off timer works. It will not go back. If it finds the medium busy, it will not go back to and choose another value from the back-off window. No. And why is that? Why is it doing that? Because in this case, if the device keeps going back to new timer every time, it will take a very long time to reach 0 and to send the information. Okay, it will take a very long time, and we don't want the device to wait for that long. Another advantage of freezing the timer is that in this case, the timer, let's say, is, in this case, is 6, right? It has frozen at the value 6. Now another machine could also be trying to send, and that machine found the medium busy, so that machine also now has a timer. But maybe the machine has got a timer that is more. Okay, so in this case, this device, the more it waits, okay, the higher the priority becomes. Okay, it's now having a higher priority. So when it waits for 6, it freezes at 6. When the medium becomes free, the timer goes back to 5, 4, 3, 2, 1. So soon the device will have access to the data, and then it will transmit the information. Okay, so this is how it works in the DIFS basic mode. Let's look at another example now. In this scenario, we are looking at collision. Okay, when there is a collision between Sue's and Mira's machines. Now, at this point in time, Sue wants to send a frame. So what does it do? The machine, it waits for DIFS, and it also chose a timer value for back-off. So it waited for that time. Okay. Now, while it is waiting, Mira's machine also decides to send a frame. Now and waits for a DIFS time. But look what has happened. Even though Mira's machine came in after Sue's machine, if Mira's machine decided after Sue's machine to send the packet, but Sue's machine chose a bigger timer and Mira's machine chose a smaller timer. Okay, this is random. this is just random values. So by chance, Sue chose a bigger timer and Mira chose a smaller timer. And because of that, the result was that they end up having the same time when their timers reach 0. Sue's and Mira's timers reach 0 at the same time. They both try to send data at the same time, and there is a collision. Okay, so after the SIFS time period, no acknowledgement is received by Sue's machine. No acknowledgement is received by Mira's machine because there is a collision. So Sue now will wait. So actually in this figure, it should show in here that it waits for a DIFS amount of time. That's important. Okay, waits for DIFS, and then it will choose a back-off timer. And similarly, Mira also is waiting for DIFS and then choosing a back-off timer. Okay, so we have DIFS plus back-off. Okay, but Sue's machine again chose a larger timer value. Mira's machine chose a smaller timer value. And because of that, Mira's machine's timer reaches 0 first, and Mira is now transmitting the data. At this time, what will happen to the timer for Sue's machine? The timer will freeze. Okay, at this point in time, the timer will freeze, and then after the acknowledgement is received successfully, maybe somewhere here, when Mira's machine receives the acknowledgement correctly, then at this point in time, Sue's timer will decrease, go to 0, and then Sue will be able to send the data as well. Okay, so this is another scenario for the basic mode where we have seen what happens in terms of the collision. The next concept we will look at is the hidden station problem.